Hello, in this video we're going to talk about how the enthalpy change of a reaction compares to the total internal energy change of a reaction, how delta H compares with delta U. And as the title slide here suggests, they're usually pretty close, but not always, so we should talk about that. So we'll just jump right into an example problem. So say you have sodium reacting with water to make sodium hydroxide, hydrogen gas, and some smoke and flames. And so the delta H reaction here is 367.5 kilojoules per mole. It's negative because it's an exothermic process. So just thinking about this first, the hydrogen gas is created from the water, and so it must make its volume somehow. It has to push back the atmospheric pressure in order to make this new gas volume. And so that is work. That's gas expansion work. Whenever you create a gas where there wasn't a gas before, that's some non-negligible work component that we need to think about. So our internal energy is going to include both the heat released and the work done to expand this gas. So to do this problem, let's start with some assumptions. So if I were to write a problem, I would specify a temperature and hopefully specify 1 bar of pressure. So this puts us at the standard state that the degree sign references, so that all works out. And then I'm going to do this for 1 mole of the reaction as written, which if you look up here, there's a 2 in front of the sodium. So that means we're going to react 2 moles of sodium plus 2 moles of water to make 2 moles of sodium hydroxide and 1 mole of hydrogen gas. So if you want to be specific about it, if you start with 2 moles of sodium, here's the mole ratio, you're going to make 1 mole of hydrogen gas. And then we're going to need the volume of this because we're going to deal with work, which needs a final and an initial volume. And so you use PV equals nRT with this, and you get your volume of your reaction to be 24.8 liters. All right, so now I just scooted these two numbers up to the top of the slide so we have some more space. Then we're going to start with the definition of enthalpy when we do this. So here's the definition of enthalpy. And well, we have enthalpy change for this reaction. It's given in the problem, but we want to calculate now the total internal energy change. So we're going to rearrange it for delta U. So now this step's an interesting one because we've gone from just kind of a hypothetical, oh yeah, whatever delta H is, now down to a concrete, here's how much enthalpy change you have for your particular reaction. So the one up here is kilojoules per mole. And then the one down here is going to be in just kilojoules because you now are specifying a number of moles. Our mole, it's going to be 1 mole of reaction because we're specifying it that way. But we are going to go from a generic kilojoules per mole to now a specific this many kilojoules. Okay, so now here's how we do that with the numbers we have. So this comes from the delta H that's provided in the problem, and then the stoichiometric coefficient of the hydrogen here, because delta H of the reaction says negative 367.5 kilojoules per 1 mole of hydrogen. And then this is the specific reaction that we're running. We said, all right, today we're going to do the reaction such that it makes 1 mole of hydrogen gas. Now, another thing we could have done here is we could have done this. We could have used the same ratio, except now with moles of sodium, and that we started with 2 moles of sodium, right? Because these ratios you can use with any of the components of their balanced reaction. And, well, now we had 2 moles of sodium that we're running in our reaction today. So you could use either one of these, and it's okay. So that's that side. That's the enthalpy change for this particular reaction. And then over here you have the work. And so P, V, and then this bit here that I slid in, this is the first time I've shown it in this unit setup. But this is what we were doing before by saying 101.3 joules per liters atmospheres. What we did here is instead we used the bar version. So we said 100 exactly joules per liters bar. And then we converted it to kilojoules, where it's 0.1 kilojoules per liters bar. And so now we're using it in the equation down here. Okay, So now that we've explained all of those points, we can calculate this, and we get negative 370 kilojoules per mole for delta U. So delta H is negative 367.5, delta U is negative 370. So they're very similar in this case, but delta H is smaller than delta U for this reaction because, well, some of the internal energy is used to expand the gas, and then the rest of it is released as heat. So the total amount of internal energy, some goes to work, most of it goes to heat, so therefore the heat value is less than the total internal energy. So this is generally true for any reaction that results in more moles of gas than it started with. Overall, you have an expansion of your amount of gas in your reaction. Your total internal energy is going to go towards both enthalpy and work. On the flip side, if your overall moles of gas in your reaction are less than where you started, it's the other way around. And then if you have a reaction where the number of moles of gas doesn't change at all, or it doesn't involve gases at all, then the change in volume is pretty much zero. And this whole second piece here that involves the change in volume goes away, because this is zero. And in this case, delta U and delta H are equal to each other. So then one thing I want to point out is you can do this problem a little more simply, at least with less steps, by rearranging your equation. So if gases are produced, work is done, this is the equation we were just using. And what we did is we used PV equals nRT to find volume. Well, instead of doing that, you can just swap out PV for nRT like this. And then you have this equation here. And then, assuming the temperature is constant, which is kind of a weird assumption to make, but you kind of have to do it in order for the math to be reasonable. Assuming the temperature is constant, well, and R is a constant, then you just have the change in number of moles of gases. And so you can use this equation all you want. Just be careful that delta N is only including the gases, because if you make a mole of gas, it's 24 some odd liters. If you make a mole of solid, it's a tiny, tiny amount that you can easily neglect the work required to create it. And then delta N mirrors the process of finding delta V. You have final, which is product, minus initial, which is reactant. And you're looking at just the moles of gases again. So you can use either one of these versions of doing this problem. It'll work out just fine. I personally prefer this one since it's a lot simpler, but you can do whatever you would like. So that's the new content for this video. So now what we have left is just a couple example problems. So in this problem, we're looking for the total change of energy, delta U, when exactly 1 mole of hydrazine is converted to 2 moles of water at 1 bar and 300 Kelvin. So you're given the reaction, you're given the delta H value for this reaction as written, and we're going to assume a constant temperature, otherwise it gets to be a whole mess. And here's the gas law constant. All right, so we start with the equation we're going to use, and I'll use the one from the previous slide because I think it's a little easier to use. And you can write this equation either with or without the little degree symbols. The equation holds either way. Here, since we're using the degree symbols and we're at 1 bar, I'm just going to throw them in here to be consistent. Now, we want delta N, and that's listed as product gases minus reactant gases. And we're looking at just the gases. So in this case, we ignore the hydrazine when we calculate delta N. And, well, we have 3 moles of product gases, the nitrogen plus 2 moles of water, and then 1 mole of reactant gases, the oxygen, and skip the hydrazine. And so this makes 2 moles. And so the reason why we can pull just the stoichiometric coefficients here, it's because the problem says exactly 1 mole of reactant is converted. If the problem said a different amount of hydrazine, then that's a whole nother problem that we get to in the next example. But for now, we can just say, great, we can use these stoichiometric coefficients, and that works out. Because in this reaction, we actually are producing 1 mole of nitrogen and 2 moles of water. So now here's the delta U equation again, and I threw the subscript Rxn in. That's kind of optional whether you include it or not, so I just decided to put it in. So here's the delta H, and this fraction here is true for this reaction no matter how much of it you're actually doing. And then we're going to multiply it by the amount of reaction that we're running in this problem, which is 1 mole of reactant. And now then there's the RT delta N term. So here's the first term here. And then for R, we use the gas constant. It's easiest just to use the one in joules. You can use one in bar or atmospheres if you'd like, but then you have to convert out of the pressure units into energy. So it's easier just to use the conversion factor where that's already been done for you. All right, 300 Kelvin. Then here's the 2 moles that we just calculated. So, all right, we're getting there. But there's still one thing left. If you look at the units here, our second term is in joules and the first term's in kilojoules, and we got to make that match somehow. So I'm going to convert the second term to joules, and then when I do that, then I can do the subtraction here and get negative 539 kilojoules. So in this reaction, the total energy change includes energy that's released as heat, which is the majority of it, and then energy that's released in the form of the gas expanding to do work on the surroundings. So there we go. All right, so now let's try this again, and instead of 1 mole of hydrazine, we'll have some odd amount of hydrazine that then we have to calculate how this would go with actual specific amounts. So the overall process is the same, but now instead of throwing in 1 mole here and 1 mole there, we actually need to calculate the amounts. So that adds some complexity to the process, but not to the concept of what we're doing. So let's do some preparatory work here. So here's the mass of hydrazine, and let's convert it to moles. There's the molar mass of hydrazine. So here's how many moles of hydrazine you have. Okay, so we'll need that number later. We're also going to need to know the moles of all the gaseous products so we can figure out the delta N for gases for this reaction. So stoichiometry can convert the moles of hydrazine to the moles of the other reactant, oxygen. That's pretty straightforward. You can do a similar process and get the moles of nitrogen, and then a very similar process and get the moles of water. Now, since there's a stoichiometric coefficient of 2 for the water, you're going to make twice as many moles. Now then, delta N is products minus reactants, gases only. So we have nitrogen and water, and then we have subtract oxygen. Products minus reactants, final minus initial. So then you do this math, and you wind up getting this many number of moles, 0.892 moles. All right, so let me rewrite these numbers here. And then here's the equation we're going to use. Again, I like to use the RT delta N format for these type of problems just because it saves a step. And then here's the conversion factor between enthalpy produced and moles of the reaction. And then this is how many moles of the reaction we're actually running. And then minus RT delta N. And so now let's compute the first part here and then work on the RT delta N. So here's R. Here's me converting the R to kilojoules so that I don't have to do that conversion later. Here's T. Here's the delta N from the top of the slide with 3 sig figs on it. Now I'm showing this where I work the left term and then work the right term. And the reason why I'm doing that is because I can't fit it all onto a slide. So I kind of work the left side, then work the right side because it fits. Please feel free to do it all in one step. That's what I would do if I wasn't making it squeeze onto a slide. Okay, now we can compute this thing. So here's the left term, here's the right term, and then you subtract and you get 240 kilojoules. And then to be thorough about it, you should convert that into scientific notation so you know that that 0 is significant. But negative 240 kilojoules of total energy change, of which 238 kilojoules of that was released as heat, and then 2 kilojoules was used to expand the gas against a constant external pressure, which does work by the system on the surroundings. Okay, so that's what we have for this video. Let me end with a summary. This chapter is an equation soup. We have all kinds of different equations and variations and everything running all around. And it seems like there's going to be a boatload of equations on the info sheet, and there probably will be. But do realize that all the problems we've done so far in this chapter came from 3 separate equations. Total energy is heat plus work. a definition of what work is, and our definition of enthalpy. And then we use the ideal gas law as well. And then if you mix and match all these equations together, you can do everything we've done so far in this chapter. So just try to remember that we're really starting with a few fundamental ideas and then just playing with them in different ways. Cool, that's what we have. Thanks for watching.